Welcome to Learning with UNP. In this session of data science and mastering machine learning, we are going to understand about support vector machine practical implementation on a project. In here, we are going to use SVM to solve a regression problem. The objective of this project is to build a predictive model using the support vector machine SVM algorithm to predict the concrete compressive strength based on various input variables. By analyzing specific features from a dataset, we aim to determine the resulting strength of the concrete mix. Let me give you an overview of what exactly we will be doing in this project. In this project, we will write Python code to implement each step of the machine learning process. This project involves several key steps: loading and exploring the dataset, splitting the data into training and test sets, building and training the SVM Regressor model, and evaluating the model's performance using appropriate metrics. We will utilize a concrete dataset which contains various predictors to train and test our model. All coding will be done using popular libraries such as Pandas, NumPy, scikit-learn, and matplotlib. Let's begin with understanding the dataset. Concrete compressive strength, a key measure in civil engineering, depends on its age and the mix of ingredients used. This dataset has 1030 number of instances and includes 9 number of attributes in which 8 inputs are quantitative measures of ingredients and age and 1 output is concrete strength. There is no missing data, making it suitable for regression analysis to predict the strength based on other variables. Now, let's look at the variables along with explanation of each variable. Cement, amount in kg per cubic meter. Blast furnace slag, amount in kg per cubic meter. Fly ash, amount in kg per cubic meter. Water, amount in kg per cubic meter. Super plasticizer, amount in kg per cubic meter. Coarse aggregate, amount in kg per cubic meter. Fine aggregate, amount in kg per cubic meter. Age, number of days, 1 to 365 since mixing. The output variable is the concrete compressive strength measured in megapascals MPa, which indicates the load-bearing capacity of the concrete. To begin our project, the first step is to load the concrete dataset into our Python environment. We will use the Pandas library, which is widely used for data manipulation and analysis in Python. Below are the detailed steps and code to load the dataset. First, we'll import necessary libraries like Pandas and NumPy. Then, we will load the dataset from a CSV file into a Pandas data frame, which allows easy data manipulation and exploration. Finally, we will inspect the first few rows of the data frame to understand its structure and content. Here is how we import libraries. NumPy has NP for numerical operations, Pandas has PD for data manipulation and analysis, Seaborn has SNS for statistical data visualization, Matplotlib to display plots inline in Jupyter notebooks. Now, we load the concrete dataset into a Pandas data frame using the read_CSV function specifying the file path. This allows us to easily manipulate and analyze the data. In here, data.shape gives the number of rows and columns in the dataset data. This output indicates our dataset comprises 1030 rows, which are instances, and 9 attributes, which are columns. These 9 attributes include 8 features such as the amount of cement, blast furnace slag, fly ash, water, super plasticizer, coarse aggregate, fine aggregate, and age, along with one target variable indicating the concrete compressive strength. Before using the SVM algorithm, you may need to pre-process your data if required. This can include cleaning the data, handling missing values, and encoding categorical variables. This line of code checks for missing values in each column of the data frame data and sums them up. In this dataset, there are no missing values in any of the columns, as indicated by the output of zeros for each attribute. After checking carefully, we found no missing values in our dataset, meaning all entries have all the necessary information. Also, all the data is in numbers already, so we don't need to change anything about how it is stored. This allows us to proceed directly with applying the SVM algorithm without needing to handle any missing data, thereby simplifying our pre-processing steps. Now, let's move on to the next step of separating features. To prepare our data for the SVM regression model, we need to separate the features from the target variable. The features X include all the ingredients and age of the concrete, while the target variable Y is the concrete compressive strength. We do this by creating X, which contains all columns except concrete compressive strength, and Y contains only the concrete compressive strength column. This separation is essential for training the SVM model as it allows us to provide the algorithm with the input data X and the corresponding output labels Y separately. Here is the code of it. Now let's look at train, test, split method. To effectively evaluate our SVM regression model, we split the dataset into training and testing sets using the train, test, split function from the scikit-learn.model_selection module. This process creates four arrays: xtrain, ytrain, and xtest, ytest, xtrain and ytrain. These arrays contain the features and target values for the training set, which is used to train the SVM model. Xtest and ytest. These arrays hold the features and target values for the testing set, which is used to evaluate the model's performance on unseen data. We use the test size parameter set to 0.3 to allocate 30% of the data to the test set, with the remaining 70% going to the training set. The random set parameter ensures that the data split is reproducible, meaning the split will be the same each time we run the code with the same value for consistency. This method helps us train the model on one portion of the data and validate its performance on another, ensuring the model's reliability and effectiveness. The code of it is shown here. Over here, let's look at model building. In the context of support vector machine SVM, there are two primary types, SVM Regressor and SVM classifier. The choice depends on the dataset and analysis goal. Since we aim to predict continuous values, that is concrete compressive strength, we will use the SVM Regressor. We start by importing the necessary libraries from scikit-learn.svm, including the SVR module, which enables us to implement support vector regression SVR for regression task. This import provides functionalities for constructing the SVR module, fitting it to our training data, predicting outcomes, and evaluating model performance. Next, we initialize the SVR model with a linear kernel using SVR kernel is equal to linear. This configuration set up the model to fit a linear relationship between the input features and the target variable. In support vector machines SVM, different types of kernels can be used to transform the input data into the required form. These kernel types include linear polynomial poly, radial basis function RBF, and sigmoid. Each kernel type serves a specific purpose and helps in capturing various patterns and relationships in the data depending on the complexity and nature of the dataset. Once initialized, the SVR model is trained using the training data, xtrain and ytrain. During this process, the model learns the relationships between features and the target variable, adjusting its internal parameters to optimize prediction accuracy for new or unseen data points. This training step is crucial for preparing the model to make accurate predictions. After fitting the model, it can make predictions on new data. Using the test data xtest, the predict method applies the trained model to estimate the target variable ypred. These predictions represent the model's best estimates for each input in the testing dataset. This data frame compares the predicted values ypred with the actual values ytest from the testing dataset. By visually inspecting this comparison, we can evaluate how closely the SVR's model's predictions align with the actual outcomes, providing insights into the model's accuracy and areas for improvement. This step is crucial for assessing the model's performance and making informed decisions about its deployment. Let's move on to understanding the evaluation metrics. To evaluate the model's performance, use metrics such as mean absolute error (MAE), mean squared error (MSE), R squared, and other metrics. These metrics will help you understand how well the model is predicting the target values. The R squared score function from scikit-learn.metrics computes the R squared score of our SVM regressor model by comparing the predicted values ypred with the actual values ytest. It measures how well the model's performance approximate the actual data points, providing an indication of the proportion of variance in the dependent variable that is predictable from the independent variables. Here is the code of it, which yields accuracy as approximately 48%. The mean absolute error function from scikit-learn.metrics calculates the mean absolute error MAE between the predicted values ypred and the actual values ytest. This metric measures the average magnitude of the errors in a set of predictions without considering their direction, providing an indication of the model's accuracy in terms of the average absolute difference between predicted and actual values. This is the code of it, which outputs approximately 8.48. The mean squared error function from scikit-learn.metrics calculates the mean squared error MSE between the predicted values y-pred and the actual values y-test. This metric measures the average of the squares of the errors, providing an indication of the model's accuracy in terms of the average square difference between predicted and actual values. Here is the code of it, which yields accuracy as approximately 148.05. By computing the root mean squared error RMSE from the mean squared error MSE, we obtain a measure of the average magnitude of the errors in the same units as the target variable. This involves first calculating the MSE with mean squared error y-test y-pred, then taking its square root using np.square root of MSE, which gives us the RMSE. This is the code which outputs approximately 12.167. The mean absolute percentage error function from scikit-learn metrics calculates the mean absolute percentage error MAPE between the predicted values y-pred and the actual values y-test. This metric measures the average absolute percentage difference between the predicted and actual values, providing an indication of the model's accuracy in terms of the relative error. The MAPE can be expressed as a percentage by multiplying the result by 100. Here is the code of it. We create a scatter plot showing the relationship between the amount of water in the concrete mix and the concrete compressive strength. The plot displays the actual test data points in blue and the predicted values from the SVM Regressor model in red. This comparison allows us to visually assess the model's prediction accuracy against the actual outcomes. If the SVM model's performance is not satisfactory, adjusting the kernel type can help. Experimenting with different kernel types like linear, polynomial, RBF can improve the model's fit. Finding the right balance can enhance the model's accuracy for predicting concrete compressive strength based on the dataset. This is all about today's lecture. See you in the next lecture. Thank you.